The Siemens team in the Nephele project delivers a solution based on intelligent and customizable IoT devices designed to enhance energy efficiency in buildings. Imagine a multinational company aiming to cut energy costs and meet sustainability goals. To achieve this, it deploys the Nephele solution, featuring advanced energy management and dynamically controlled HVAC systems that activate only in occupied spaces. Presence prediction, integrated into IoT devices like Siemens Target 5, uses tiny machine learning and a micro-complex event processing engine to locally process sensor data, for example, temperature, humidity, CO2, for occupancy detection, enhancing efficiency while preserving privacy. Target 5 devices follow the W3C Web of Things standard for seamless integration with existing building systems. They can be orchestrated via the Nephele meta-orchestration framework and are deployable across the edge cloud continuum. In this demo, we'll show how Nephele technologies are used to build the energy balance application using so-called composed virtual objects. We begin by developing the firmware for an IoT device using Platform 5. This firmware integrates TinyML and a micro-C EP engine, two core components that enable local intelligence. Once the firmware is ready, we deploy it onto a Target 5 device. From there, we define the TinyML model and the CEP rules that form the heart of the application logic. To ensure seamless integration with existing building systems, we enable interoperability by following the W3C Web of Things standard. This guarantees that the energy balance solution fits smoothly into broader building management environments. Now, we'll show how to build an embedded energy balancer application using Platform 5 and deploy it on our Target 5 device. We start by selecting the STM32F777 board used in this setup. The firmware includes essential components like a database, CLI, Modbus, TCP/IP stack, and a control chart for application logic. For the energy balancer, we add three key modules: TinyML, a micro-C EP engine, and MQTT. These components are developed as reusable assets within Platform 5. Next, we configure all components and build the firmware. We then design the application logic by integrating a TensorFlow-like model that predicts room occupancy based on CO2, temperature, and humidity. We follow this by adding the micro-C EP engine to implement rule-based energy balancing using the model's output. Specific rules will be added later. Finally, we generate the firmware. Now, let's engineer the application logic using TinyML and micro-C EP engines, integrating sensor data seamlessly into the system. We will upload a TensorFlow model capable of detecting room occupancy based on temperature, CO2, and humidity data. This will be followed by integrating a micro-C EP engine to control the HVAC system accordingly. Finally, we generate the embedded project that can be flashed to the hardware. Now, let's realize the energy balancer application using the created firmware. On the left, you see a simplified version of the application logic. If room occupancy is detected, we check the CO2 level. If it's below 1000 parts per million, indicating good air quality, the HVAC fan runs at 50%. Otherwise, it switches to full power. On the right, you see how this logic is implemented using micro-C EP rules, enabling real-time, rule-based control directly on the device. Now, we flash the project onto the Target 5 device. Shown on the right inside a 3D printed black enclosure. This device is equipped with CO2, temperature, humidity, and radar motion sensors. It connects to an IoT Edge device for MQTT. The Edge hosts the virtual representation of the Target 5 and its application, and also facilitates the transmission of micro-C EP rules from a laptop to the embedded device. Let us start the application and see the printed output of the serial port. On the left, we see raw sensor data along with occupancy inferences from the tiny ML model. On the right, a simple MQTT client is used to send micro CEP rules to the Target 5 device. Once the 3 rules are uploaded, new events appear immediately. Since the current CO2 level is 524 ppm and the model inference is below 50, the system issues a command to run the HVAC fan at 50% speed, indicating good air quality in an occupied room. If a person is detected in the room, the system instructs the HVAC to operate at full speed, 100%. This ensures optimal air circulation when the space is occupied, maintaining comfort and air quality. Finally, let's explore how Nephele ensures interoperability across devices using different protocols, based on the W3C Web of Things standard. We begin with the Smart Energy Balancer application graph, deployed by Odin-S. Most devices are integrated as virtual objects over MQTT, except one, a Siemens radiator valve actuator using IPv6 and the thread protocol. This actuator is wrapped in a thing description-based virtual object, making it accessible via a unified HTTP interface like any other Odin-S device. Here, you see the Odin-S dashboard displaying sensor data from a room. To integrate new devices, simply place their thing descriptions in the Things directory. Siemens Web of Things Servient automatically discovers them and exposes their interfaces via HTTP and WebSocket. For example, the thing description of our actuator shows its IPv6 base URI using CoAP, along with metadata and supported properties. The Servient user interface lists all known things, Odin-S devices, and the Siemens actuator. Opening developer tools for an Odin-S virtual object reveals a unified HTTP or WebSocket interface. Despite different underlying protocols, all devices now expose their properties uniformly. For instance, CO2 values are returned as standardized W3C JSON objects. The Siemens team has successfully integrated Nephele's key results into Platform 5, an end-to-end solution for constrained IoT devices in building automation. Platform 5 offers reusable hardware and software components, firmware engineering, and mobile app support. Nephele's tiny ML and CEP engines, along with W3C thing descriptions, align perfectly with Platform 5's strengths. They enable the creation of customizable, intelligent IoT devices with standardized interfaces for seamless integration. Siemens engineers will leverage these assets in future commercial IoT products for the building sector.